Hello everyone and welcome back to this lesson. In this video, we will take a look at different setups in which you can fine-tune your LLMs, and we will see how these different setups affect the GPU memory that you need. So throughout this video, we will be working with LLaMA 3.18 billion, and we will look at different things that we can do. For example, we can do full fine-tuning. We can apply LoRA or QLoRA, so how each one of these affect the GPU utilization. What's the difference between full precision and half precision? We can also simulate having more GPUs. So what if we have one or two GPUs? You can change the batch size, sequence length, all these things. So there are endless combinations that you can do here. We will look at 4 different scenarios and try to understand the differences between them. And we'll be using this tool for this video. We will have the link in the lesson. One good thing about this is that it breaks down the memory you need for you into different categories. For example, how much memory is needed for activations, gradients, optimizer state, and so on. So we'll take a look at the different scenarios and see how each one of them affect the memory in its own way. So the first scenario we'll look at is full fine-tuning. In this case, we will not be doing any kind of optimization or any tricks to try to reduce the memory, and we will see how much memory we need in this case without doing any tricks. The second one would be try to do some optimizations, but we will not be applying any parameter efficient fine-tuning methods like LoRA or QLoRA, so just a simple optimization tricks. The third one we'll apply LoRA, and then fourth one we will apply QLoRA, and we'll compare these against each other. So the first thing is full fine-tuning. Let's say we have an 8 billion parameter model. We want to do full fine-tuning and full precision, and we will be having a single GPU that has 80 gigabytes of VRAM, this is a very expensive GPU. And let's keep it as one GPU for now. For batch size, let's stick with something realistic, something like 8, for example. Let's assume 2000 sequence length, for example. This is a setup that does not have any tricks. We're not trying to optimize for anything. It's a very simple setup. And you can see that in order to fine-tune an 8 billion parameter model, you need approximately 160 gigabytes, which is twice as much VRAM as you have here. So in order to run this way, at least you're going to have to increase GPUs. So you're going to have to add one. Even if you add one, you're still more than 160. So utilization is over 100%. So it's not going to be possible. At least you should have 3 GPUs in order to run something like this. Even though the model size is considered small compared to the numbers that we hear recently. So you have models that are 70 billion parameters. You have models that are over 400 billion parameters. So these are giant models. So a model like this is considered small compared to these things. And you should know that even a small model like this, if you're going to fine tune it in this setup where you don't apply any kind of tricks or try to reduce the memory, it's going to require a lot of memory. At least you're going to need 3 800 GPUs in order to run something like this. And yeah, keep in mind that increasing the batch size will always increase the memory that you need. Similarly for sequence length. These parameters always affect the memory that you need, but we will not be playing with it. I'm going to keep it fixed for all the different scenarios that we will look at. Feel free to open up this tool and try to play with these values and see what you get. So now let's say you want to try to bring this number down a little bit. The first thing you can do is to use half precision instead of full precision. And you might expect that this number gets down to 80 or something because now you are only using half the memory you need. You are right that this number is going to drop, but it's not going to be dropped by half. Previously it was 160, now it's 120, so you saved like 40 gigabytes, which is huge. And the reason why it's not cut off exactly by half is because the precision does not affect the activations nor the optimizer states. These will be in full precision anyway, and mainly the 2 things that are affected are the model weights themselves and the gradients. In half precision, you can see these are 16. And if I bring it back to full precision, now they are 32. The reduction is happening here, but these numbers remain the same. And that's why it's not exactly by half, but you can see it's a huge reduction. So if you do this, at least now you can fit this model with this setup only on 2 GPUs. It can be trained comfortably. The next trick you can do is to enable gradient checkpointing. So gradient checkpointing is a technique that prevents the model from storing all the activations until the back propagation step. all neural network models, they work by performing a forward propagation. And then during that, activations are computed. And then you use them in order to perform the backward propagation to update the model weights. And applying gradient checkpointing basically means that you will not be storing all the activations that you need for the backward propagation. You'll only store some of them. And when you need them again, you will recompute them. It's as simple as you already had them, but you don't want to keep them in memory. So you ignore them and then recompute again. So it's just a trade-off between compute and memory. So you don't mind that you recompute the same thing again, but reduce the memory requirement. If I enable this, you'll see this number is going to be reduced a bit. So now it's reduced from 100 and so yeah, we basically save 2 gigabytes. You can see the less you're going to make this parameter, the more memory you are going to save, because it means that you are storing less activations during the forward propagation. And then finally, you can change the optimizer itself. Instead of working with the normal Adam optimizer, you can work with an 8-bit optimizer. Keep in mind that the optimizer is the component that takes most of the memory here. So 57% is just for the optimizer. And this is a full precision optimizer, meaning every state here is 32 bits. So what if we reduce it to be an 8-bit? You would expect this number to go down in a huge way. If you do this, you can see now it's taking 17 gigabytes instead of 65. And now you only need 64 gigabytes of VRAM, which means this setup can be achieved using a single A100 GPU. So let's take a look at parameter efficient fine-tuning methods. Keep in mind the setup where we did full fine-tuning without any kind of tricks. We needed 160 gigabytes. And now if we do LoRA, you'll see this number drops drastically to 30 gigabytes, which means you can even get a smaller GPU than this and it would still work. And the reason why this is happening is because LoRA freezes the model weights and it introduces new matrices, typically 0.5% of the total model parameters. And these are the only ones that are fine-tuned and the ones that the optimizer has to keep track of their state. Because the number of parameters is very less compared to the original scenario, you get this huge reduction in size when you use LoRA. So when you apply LoRA, you would have to choose some rank. You need 30 gigabytes if you're using a rank of 16. But even if you double this number, it's not going to cause like a huge increase in memory because most of the model weights themselves are frozen. And the new parameters that you are introducing here is just a tiny fraction of the model weights. So even if you double this, for example, so if you do 32, you can see it's a very minimal increase in memory that you need. Okay, so now let's do a QLoRA. So the difference between LoRA and QLoRA is that QLoRA quantizes the model weights themselves. So instead of the parameters being stored in 32 bits, they will be stored in 8 bits. So you would expect a huge kind of reduction. But again, these affect only the base model weights. Activation is going to be the same. And the optimizer state is going to be the same as well. If we do QLoRA here, so before we do it, here the base model weight is 16 gigabytes. And here we are using half precision. So when you do QLoRA, it's going to be in 8 bits, which means the model size is going to get cut by half. Sorry, here it's using even 4 bits. You can see the base model weights, instead of 16, now they drop to 4. We reduced the model size 4 times. And you can see we saved like 10 gigabytes of VRAM by moving from LoRA to QLoRA. Here we are just applying QLoRA. Keep in mind you can do all other optimization things like using flash attention instead of the vanilla attention. You can do gradient checkpoint. You can even untize the optimizer itself. This would reduce the memory even more. And there are different kinds of things you can do. You can play with the batch size, sequence length, and all kind of stuff. The idea of this video is to first try to appreciate the parameter efficient fine-tuning methods, because without these, there is basically no way that you can fine-tune a model like this on a 20 gigabytes or 24 gigabytes of VRAM GPUs that you would have normally on your PCs at home. And also to see that full fine-tuning actually requires a lot of resources. Even an A100, which is an 80 gigabytes GPU and one of the most expensive GPUs out there, is not capable of fine-tuning an 8 billion model unless you have at least 3 of them, which is a huge number of VRAM in order to fine-tune a model like this. That's it for this video. I hope you found that useful. and I'll see you in the next one.